We're going to begin Unit 2 with a review of the history of science a little bit, but more specifically the history of evolutionary thought and its origin. Now, what we commonly call science today really is rooted in ancient Greek philosophy. And there were a number of ancient Greek philosophers, many of which we don't have a very detailed record for. Empedocles is one of these. You don't need to know that name, but these philosophers began to lay the foundation for what would become scientific thought. And so they were interested in the world around them and how it worked. They had some ideas that today we would kind of laugh at or think were a little superstitious, things like that. But there were some of them that began to look at the world around them and talk and write and think about trying to explain what was going on. So Anaximander is one of these. Again, you don't need to know this name in particular, but just as an example. So Anaximander came up with this idea about how the world worked, and he wrote about this and talked about it with other people and taught people about it. And basically, it's a hypothesis, and there was some data, but they had very limited resources and limited methods by which they could confirm or gather support for what they thought. So here we have this idea that the Earth is a flat disk with a bubble of air on it, that the universe that we're seeing around us is actually a black disk with lots of holes in it. Those represent the stars. There's a giant fire outside, keeps everything warm. Sun and moon are inside that. They go around the Earth. And so he started to come up with these ideas. And again, today we'd look at that and say, well, that's not a very well-supported idea. There's not evidence for that. We have evidence for different ways that this works. But this is a beginning, and that's how science starts. It starts as somebody with an idea, with a hypothesis. And then we gather data. We think of ways that we can test whether or not that hypothesis is correct. And so obviously, as things have moved on, these things have been tested, many of them rejected, but the point is it's beginning. And at the time, they didn't call it science, as it's been termed methodological naturalism, but really it was, an early primitive version of science. So the first name that you need to know is Aristotle. And you may already be very familiar with Aristotle. In many ways, he's thought of as the father of modern science, certainly at least natural history, but actually many other types of science. And his influence was vast. Many of his writings survive. Many of the people that he taught went on to continue his work, and he established a foundation for classical Greek philosophy, and which led to our modern science. Now, many things that he did, we don't have time or need to go over a large portion of them. We're just going to highlight one, which is his idea of the scala natura. Now, scala natura was the first written, at least the one that we have recorded and has survived. So the first idea about how we classify and organize life on Earth. Now, we know today that we have this classification system where we have species organized into genera, genera then organized into families, and so on up the line. And it helps us to not only have a common system that we can talk about and reference when we're looking at organisms, but it also allows us, and has allowed us in modern times, to put those genera and families and so on into a proper evolutionary perspective. Now, Aristotle's idea was a little bit simpler, and it was this idea that we can put all organisms on a ascending ladder. In fact, in Greek, scala natura literally means nature's ladder. And so he put plants on the bottom, and then simple organisms, and then more complex organisms. We've got birds here, and then we have, I think, mammals and birds actually on the same level there. Looks like fish there. So, there are different versions of this, and it's obviously not a very subjective way. Is a bird more complex than a lizard? Is a lizard more complex than a mouse? How do we determine that? But of course, there's also some political and social structure here also, because we have peasants on one level. This is not Aristotle's, but this is a later version using the same idea. And then we have the upper class, right, the aristocrats, angels, and God on top. So it was a very political and oftentimes a charged way to organize things. However, for the natural part, it was a first attempt to do this. Now, we recognize today that this is not a very useful or accurate way for us to organize life on Earth. So I want you to recognize that we don't use this today, but it was a beginning, and it held sway for thousands of years, all the way up until Darwin and his ideas begin to replace this idea of a scala natura. Now, Aristotle did lots of other things. He did some of the first, at least recorded, experiments that we have. So he took chicken eggs and looked at the progress of development from the day that they were laid all the way until they hatched. And he drew those out and wrote about them and began to talk about development and wrote down ideas about that. Now, after the Greeks, there is long periods of time where there was, excuse me, some work being done in the Middle East, and some of that survived and was recorded, primarily dealing with medicine, but other areas like cosmology, looking at the universe around them, and there was work going on in China. Again, we have some written of that. And eventually, all of that comes together during the Renaissance. And during the Renaissance, so we're talking 1600s, 1700s, going even back a little bit farther than that in some areas, we begin to re-establish a systematic way to do science. So primarily drawing on the Greeks, but also drawing on some of these ancient Middle Eastern and even Eastern texts when available. So all of this leads into really kind of our modern version of society. And all of that begins in the 1700s. Again, some of it, microscopy and other things, going back a little bit later than that. But for natural selection and evolution, we're really looking at the 1700s and 1800s when we begin to organize and draw together the ideas that are going to eventually become our modern biology. Now, there's one critical idea that we're going to draw from geologists. So Hutton and Lyell are the next two names that you need to know. We'll just treat them together. There were other people working on this also, but they are the two main and most influential names in this field. And they were geologists, but because, especially evolution, but biology is in many ways a historical science, or at least has historical elements to it, we need to know their contribution. And so even though they were geologists, they came up with this idea of uniformitarianism that is critical for evolutionary theory and evolutionary thought. So uniformitarianism, in very simple terms, is that the processes that we observe today have been going on for thousands and millions of years. And this is a rather kind of natural and simple idea, and maybe comes naturally to us, but at the time it really was remarkable that the laws of the universe today are the same laws that applied 10 years ago, 1,000,000 years ago, 1,000,000,000 years ago. The same physical principles of the universe are in effort. So gravity, the same yesterday, today, basically, so we can make inferences, right? So if we can measure rates of erosion, look at the hardness of the substrate, the rates of flow of water, elevation, and all those things, we can make inferences to things that are occurring over a much larger time scale and are a little bit more difficult to measure. So we could perhaps estimate how long it takes to carve the Grand Canyon if we understand the properties of the system. Okay, so this is this idea of uniformitarianism, and it's critical if we're going to have any understanding of the history and past events on our world. Okay, so another idea, a theory that was around at the time, was this idea of spontaneous generation. Now, uniformitarianism is a very valid foundational principle for any historical science, still the foundation today and well accepted. Spontaneous generation, on the other hand, was a hypothesis, an idea that was tested and eventually was refuted. But it's important that we understand the context. So I want you to know what spontaneous generation is, and that eventually, as we tested this hypothesis, it was refuted and replaced by other ideas. Okay, but spontaneous generation is the idea that living organisms can fairly easily arise from non-living material, organic, sometimes even inorganic. And so the classic experiment is we leave a piece of meat out, and eventually you see maggots in it, you see flies pupating and arising out of it, and people looked at that and said, oh look, flies, living creatures, came from this dead, albeit organic, but dead material. And so people began to test that idea. They put the meat in a sealed jar, a sealed container, and they say, hey look, no flies coming out. See, it's not spontaneous generation. Now, there are other processes going on at the microscopic level, even in sealed containers. But people made the argument, well, maybe air is necessary, right? We can't have a sealed environment and sustain life. So that's not a fair test. And so people devised other tests. Louis Pasteur very famously boiled basically broth, right, soup, and then looked to see if bacteria would grow in it. And he found that even if you had air, if you didn't have any way for bacteria to get in, then the sterilized material remained sterile. And so this idea of spontaneous generation with Louis Pasteur and other people was eventually refuted, but for a long time it was well accepted. And again, we kind of laugh at it today, but it made a lot of sense. You know, if you make very superficial observations, this might be an easy conclusion. So we see turtles coming up out of the sand. Now, of course, we understand that the mother turtle had to go there and put the eggs in for the turtles to come up. The turtles are not just spontaneously generating from the sand. If you dig a hole in your backyard and fill it with water, very quickly you'll begin to see it fill up with first microscopic organisms, then macroscopic algae and other plants. Eventually you may even get turtles and frogs and fish in that pond. And so you can understand that if you didn't make very careful observations and observe all the processes that led to the establishing of life in that pond, you might assume that it had arisen from the inorganic material that was there. But of course today we've tested that and we know that that's not what's going on. So we're now in the late 1700s, early 1800s, and people are beginning to think about species and where they come from. The main idea at the time was that species were immutable, meaning that they couldn't change, that they were created at some point, again, usually some creation story or creation idea. God created species and that species didn't change. But as people began observing the world around them, they realized that that wasn't the case, that in fact people very often changed species for their own purposes. They bred them selectively, and they would change them to have critical features that they like. And so people began to write about this. And so at this time there were things like written accounts of a struggle for existence, or that populations were changed. People sometimes said that they were perfectly adapted to their environment. So adaptation implies some sort of a change over time to get species to where they fit perfectly in their environment. And so there were lots of people writing about this, and we're not going to learn any of these. One of these, in fact, I think that one is actually Darwin's grandfather. But there was at least some thought and tradition, although no clear theories about how it occurred, but lots of thoughts and ideas about species and species changing in the late 1700s and early 1800s. So along comes a man named Jean-Baptiste Lamarck, a French scientist who did lots of work and was very influential and important. And he was the first person to propose a hypothesis about how species change. And so his hypothesis had two main points. Now we're going to learn these. You need to know Jean-Baptiste Lamarck's name. Know that he was the first person to put forth a hypothesis about the nature of evolution, in essence, how species changed. Number one part of his hypothesis is that there was an inheritance of acquired traits. Now what this means is that changes to the physical body of organisms could be passed on to their offspring. So for instance, and there have been people that have actually done these experiments, although today we might have ethical problems with the way that they conducted them. But if you cut the tail off of a mouse and then allowed it to breed, Lamarck would say that that shortened tail, that lost tail, would have an impact on its offspring. So, for instance, if I was to go and work out and put on 20 pounds of muscle and get in really, really great shape, and then I have offspring, Lamarck would hypothesize that my offspring would be better off and would inherit those acquired traits that I got by exercising and working out. Okay, now today we realize that that's not an accurate statement, that for the most part, with some very rare exceptions as we look at epigenetics, but that's another topic, one that we really won't get into in this course, and it's a very, very minor portion. But we realize that, you know, luckily for us, let's go back. Luckily for us, the traits that we acquire during our life cycle, so if I lose my arm, if I get cancer, that for the most part those are not passed on to our offspring. Okay, but that was Lamarck's idea. Number two is that all species on Earth were separate from one another. There were no connections, and so all species originated independently. And so Lamarck's idea was that species that were very complex, like humans, which at the time would have put very high on nature's ladder, right? Complex, um, by just about any measure. And that's a really a fair assessment if you're looking at complexity as your measure of species and species differences. But he would have said that complex species had been around for much, much longer, and that simple species had originated much more recently. And so Lamarck's second part of his hypothesis really infers that you do have to have fairly common spontaneous generation. Because if you're going to have lots and lots of species, you have to have some way for those species to originate.